This is Linear Algebra Project 1. I'm Braden Fidel.
I'm Carter Diamond.
Royce Black.
Thomas Rainey.
So for this project, the description states that using MATLAB, you want to analyze the pressure waves given with the electromagnetic pulses onto a sphere. We want to use MATLAB to plot the Fourier transform. Then we want to analyze all the data and extract it into plots, and then compare our findings. So we are going to get off into the locations. There are a total of 7 locations for this project. Since we are a group of 4, we needed 3 or more, and we decided to just do all 7. In the sphere located on the right side of the screen, you'll see that location 4 is the center, and location 1 and 7 are their outer bounds, and respectively 2, 3, 5, and 6 in between.
Alright, so starting with location 1, data. First, we took the original data and added a DC offset, as you can see in the first graph. Then we took the Fourier transform of that data, and we can see it peaks at 17k hertz. And then we selected 10 points on the original data to get an exponential dampening function. And then we added a Fourier fit to our Fourier transform, and as we can see, it's a pretty good fit right here. And then in order to get our harmonic oscillator equation, we multiplied the damped exponential function with the Fourier curve fit, and we see here that it gets a nice matching of the original data.
Similarly, we have location 2's data. We have the Fourier transform. The peak is at 17 kilohertz, and we have the exponential decay similar to the location 1, and then we have the combined curve with the Fourier and damp. There's a little bit of outliers compared to the exponential decay, but still relatively a good fit to the original.
And on location 3, our peak value for our Fourier transform is 34k hertz, and our exponential decay looks pretty good, but whenever we get to our Fourier fit, we have some outliers. And whenever we move on to our oscillation, it is way off compared to the original without DC signal, and we'll explain more about that at the end of the presentation.
Alright, for location 4, we see that the peak is at 34k hertz as well. And we see this one is probably the best exponential decay we have with our 10 points. We get a really good exponential fit right there for a damped function. And then we can see with this location as well, the harmonic oscillator equation is a little bit too high on the peaks, which we'll show at the end of our comparison.
With location 5 data, it has a peak in the Fourier transform of 34 kilohertz. And there's a little outliers on the exponential damped graph you see, and it's not that good of a fit compared to the original.
And on to location 6, we have a peak value on our Fourier transform of 17k hertz. As you can see here on our exponential damp, our 10 points here, it looks pretty good, and we have a little bit of outliers on our Fourier fit, but it looks pretty good compared to the original DC whenever we put in our oscillation.
Alright, and then finally for location 7, we see that the Fourier transform is peaked at 17k hertz. We see that the exponential damped function is a pretty good fit with minimal outliers, and then we see that our harmonic oscillator equation is a solid fit compared to our original data.
Now we're going to get over to the comparison of comparing all locations. So with what the guys mentioned in the comparison, 1, 2, 6, and 7 all peak around actually identically to 17k hertz, as you can see in these graphs when you put them side by side. And then likewise 3, 4, and 5 all peak at 34k.
So as a summary here, we talked about earlier that location 3, 4, and 5, our harmonic oscillator equation was not quite fitting, but we can see if you look at the graphs down below, these 3 graphs are the harmonic oscillator equation divided by 2, and we see that we get a lot better fit with the original data once we divide it by 2.
And in conclusion, with our locations, the more in the middle of the locations you are, the higher the frequency you are, and the more outside of the locations you are, the lower the frequency you are.
Thank you so much.